Hey, Physics 20s. Okay, so we are going to go over the next bunch of this test here, or this practice questions. Maybe we'll get over the next, all of them. We'll see. All right, so let's start. Looks like we're starting to dynamics here. Yeah, because we got some forces and stuff. Well, we had forces in the previous question. All right, so we got a system of masses as shown here, accelerating I'm going to assume that's 2.0 meters per second to the right. If the tension in the rope P is 70 newtons, that's the one in there, what is the coefficient of friction between the masses and the surface? Okay, so when we're doing a question like this, because there's multiple objects there, let me just change this. Because there's multiple objects, then we have to kind of just think about just one of those objects, right? Because if I look at the whole picture, that 70 newtons just cancels out because it's one of those action-reaction forces. So if I were to draw the free body diagram for both these objects here, so let's put the forces in here. So I got a force of normal, I got the force of gravity, I got the 70 newtons pulling me forward here, and then we got this friction that's slowing us down, right? And this object over here has got this applied force pulling forward. Don't know what that is, right? Because they only gave us the tension in point P, not the tension in the rope in the front there. We got normal force. We got gravity. I didn't label them over here. Maybe I should. All right. So those are the forces we have there. We also have the 70 newtons pulling back and the friction slowing it down, right? So that's what our picture looks like so far. So when I'm looking at this, I'm thinking, okay, it says that the two objects are accelerating at 2.0 meters per second to the right. But if I look at the whole picture, then I have all these frictions, which is kind of what we want because we're trying to solve for those frictions, and this F applied that I don't know, all right? So when I'm doing this question, I'm trying to, look at a system, zoom in, zoom out to a part that actually can be solved, right? So if I look at the first picture, can't solve it because there's F applied on it. But if I look at the second picture, that doesn't have an F applied on it. It only has the 70 newtons and the FF. I know the question says that the system accelerates at 2.0 meters per second squared, but we also know that the acceleration of one box is also going to be that 2.0 meters per second squared. Yeah. So let's see what we have here. So we got an F net. Because I put it around just that box, mass times acceleration, it's just going to be the 20 kilograms and the 2.0 meters per second squared there. Yeah. So let's do this. So 20 times 2, oops, 20. Why am I doing 20 times 2 my calculator? Okay. So we have 4D. So all the forces had to add up to 40 newtons to the right. Yep, that's what the picture says. Okay. Then remember that F net is also equal to all the forces added together. So we got the 70 newtons, we have the force of friction, we're going to add them together. That's going to end up being 40. So if I rearrange this equation for force of friction, I get my force of friction to be, if I just minus over the 70, negative 30 newtons. Again, the negative is just telling us that it's going backwards, right? So if we said forwards is positive, this is going to be backwards. Okay, so now we know the force of friction. Our goal is to find the coefficient of friction, not the force of friction, but mu. That's what we're looking for. We're looking for mu. So we're going to rearrange this for mu. FF divided by FN. Because we're on a level surface here, my FN and my FG will both be the same. So this is just going to be FF divided by FG. And remember, you can find Fg by going mass times gravity, mass times 9.81. So I'm going to have 30 divided by 20 times 9.81, and I get 0.15. That's it, 0.15. So remember, this one doesn't have any units. All right. Okay, so on the next question here, we got a baseball player exerting a force for a certain, well, it doesn't say for time period. I'm thinking physics 30 when we use time. For on a 150 gram, so we've got a different unit here than we usually have. So you got to make sure to have those proper units. So grams is not, right, what we need here, kilograms. I actually don't even know if we need to worry about that on this one. At the moment of impact, what is the respective acceleration with each of the things here? So we got a couple positive, a couple of negatives. That's good. Okay. So baseball player hits the ball. So the ball is probably going to go in the positive direction, and it doesn't really specify. Oh, it just says with a force. So hit the ball with a positive force. Now, if we know our Newton's third law here, if I hit the ball, oh, what was that? Yeah, just one second. Oh, it's getting me right to the bottom. Okay, so if I know the force in which the ball is hit at, right? That's a basketball. Okay, the baseball is being hit at here, and I know the force. Oh, okay, but then I know the force in which the baseball is being hit back at because of Newton's third law. So if I know this force is 950 newtons, then I know this force backwards is also 950 newtons. So those two forces are going to be the same. Okay, so say I did the ball. So this is positive, this one's going to be negative. Okay, so if I did it for the ball, I'm going to have A is equal to F net divided by M. You got to make sure to change these here. So we're going to change them to kilograms. I'm going to divide them by 1,000 because that's what a kilo is. Divide by 10 to the 3 each, which moves the decimal place over 3 spots. So for the ball, it's 950 divided by 0.150 gram, or kilograms now because I changed it. There you go. 950 divided by 0.15. So based on that, the answer's got to be B, right? Because the acceleration is positive 6,333 meters per second squared. Now just to double check, do I get the right acceleration for the bat? Even so, you can see that even though they are experiencing the same force, same magnitude, opposite directions, because their masses are different, you're going to get different accelerations. Yeah, so 1,187. I wonder if I can write that down here. 1,187.5 meters per second squared. It's quite a fast acceleration, but the impact is probably for a very small amount of time, so they're not going to get to too big of a speed, but it will be fast enough. Okay, force is classified as a vector because it has quantity and direction, right? So that's the key part here. Vectors have magnitude and direction, right? There's lots of different vectors out there. You can't just say they all have displacement because they don't. Some are just forces, some are velocities, some are accelerations, not all displacements. Right, so in this case, answer C. Put that over this side here again. I'll put it right there. Okay. Okay, so which of the following rectangular component vectors is equivalent to the bearing? Okay, so bearing, we don't do bearing. I can never remember which a bearing is, bearing clockwise or counterclockwise. That's from the north. Bearing method is something that we don't do, at least in my physics class. You might do it in future physics classes. There's just too many types of vectors out there. So let's see. You probably get rid of some of these here because we're looking for components. This is going to be my hypotenuse. Kind of weird way to write this too. That's my hypotenuse in the front. Why would these numbers in the front here be bigger? The components will never be bigger than that. I'm assuming this is like the X and the Y, or like the west and the north or something. Yeah, rectangular. You usually do the X and the Y first. I don't see why you wouldn't do it any other way. Yeah, we could try this. Let's see if we can get an answer. I don't know what we're going to get here. So let's see. So from the north here, going negative, I think that's going to go counterclockwise here because bearing is different. That's my guess. 168 somewhere in this quadrant down here. So there's my vector. This is going to be 35 kilometers per hour. And then we're just trying to find the components of that vector. Right? This is why we don't like using non-standard position ones, because it gets a little bit weird, because now I can't just use the 168 and say sine and expect to get the y value. Actually, if I use that, I'll probably get the x value. Right? So what's inside the triangle I drew here, this angle is going to be 90, or 180, 168 minus 90, so 678 degrees. It's like a reference angle, and then I can use that to find, like if I go sine, I'm going to get the 34, so this will be 34, and if I go cos, I'm assuming I'm going to get the other one. 7.3, let's see. Yeah, 7.3. Both negative. You can see here, you got negative, negative. If I write the x first, kind of looks like this is how you would write it. It's probably going to be b. Okay. All right, so boat X is moving at 5 meters per second. It's being passed by boat Y, moving at 8 meters per second. The man moves to the back of the boat at a rate of this. Is moving at this and is being passed by this. A man moving at the back, his velocity relative. This is another relative motion question. We don't. There's a couple of questions in here which won't be on your exam, and this is one of them. But how this kind of works is that if you're on the boat and if you're just standing on boat, so relative boat Y. So say you're standing on boat Y. I'll draw my boat Y here. Here's boat Y. Okay, and what are you doing on boat Y? You are moving at 8 meters per second. So you're just standing here on boat Y. Okay, so the boat here is moving, boat Y is moving at 8 meters per second. So how these relative motion questions work, which are not going to be on an exam, which is kind of fun and interesting. If this is moving 8 meters per second, if he was just imagining himself standing still and he was passing by someone that was moving his boat X here. Oh, that's not good. Go back down here. Yeah. Okay, so if this is boat X here, I'm going to draw boat X. And it's moving at 5 meters per second. And this one's moving at 8 meters per second. So to the person on boat Y, it looks like that boat is moving backwards, right? Because they're passing them, right? So if I look at how the question is, if I change the frame of reference to someone that's on the shore, to the guy as if he's standing still, so boat Y is now 0, right? So boat Y's velocity is, I would say, 0 meters per second. It would look like to that person, because I've just changed the reference. So I moved the reference from 8 meters per second to 0. So I'm minus 8 from everything. So now it looks like to boat Y, to a guy standing on boat Y here, that boat is now actually moving back minus 2 meters per second. Okay. But now the guy on the boat, there's another guy on the boat who's also moving backwards at so not 2, it'd be 3 meters per second, is also moving back at 3 meters per second. So to the person on the stationary boat, relative to him, it looks like that guy is moving back at 6 meters per second because he's moving backwards. So it's 2 negatives here. So my overall velocity is, I'm just going to keep this guy, I'm going to draw this guy back on here too. His overall velocity is -6. There you go. That's how it works. So I can change the frame of reference. Just like when we talk about like potential energies, 0 can be wherever you want it to be, and the same thing with these velocities. 0 can be wherever you want it to be. Anyway, let's keep on going. Let's go to questions that actually make that are useful here. Okay, so we have this color. So we have this force here at 40 degrees. It's just looking for the horizontal piece, so it's looking for this x piece here. Remember, we got x and y, and for this horizontal piece, that's the x. So to find the x, we're just going to use cos. So 80 cos 40 degrees. Pull out your calculator, making sure it's the right mode. Hopefully by now it is. And we get 61.28 newtons. So proper rounding, 61 newtons. There you go. Let's go down here. Oh, so this is a resultant. So this is finding our F net. So this is shown for overhead. The reason they say it's overhead because then we can ignore gravity, right? Gravity is like into the page. The normal force is out of the page. That's not where the direction of motion anyways. So they're just going to cancel each other out. So I'm really just adding these two forces together. So remember, when adding vectors, we don't just add them together. So this is not going to be 130, right? Because they're off at different angles, they're no longer collinear. So when we add vectors, we add our x's and y's. So what we need to do here is break these two vectors up into their x and y components, and our F net, our resultant, is going to be the sum of all those x and y pieces. So this one that's going straight up, I've got a 0 because it's going straight up, and then I got a 65 newtons straight up. Yeah, nice positive 65. But here, this 65 is now at an angle, so we got to break it up into its x and y pieces. I'm going to draw like the reference. Like I always like to draw down towards the x-axis. So I'm just going to figure out what that angle is inside that triangle. If I go 90 minus 35, and you get 55 degrees, right? So to find that, I'm just going to put a little mark here. 90 degrees minus 35 degrees. And that gave me 55 degrees. Okay. So now I'm going to use the 55 degrees. So for the x, because it's adjacent to that one, I'm going to go 55 degrees, sorry. I'm going to go 65 newtons times cos 55 degrees. And the y is the opposite from this angle. So I'm going to go sine 55. Okay. Remember, when you do these ones, if your angle is less than 90, but it's not in the first quadrant, you have to remember, is it supposed to be positive or negative? Because your calculator is always going to spit out a positive answer. So when I do the cos 55 here, I get 37.28. I'm going to put maybe a couple more decimal places here, just so I have a good number sig digs. All right. And then 65 sine 55. I get 53.2449. Okay. So now looking at this, they're both in the first quadrant. The picture's in the first quadrant here, so these are both positive. If I have my sign convention, I didn't draw my sign convention here. I probably should. Uh-oh. Oops. Oh, I messed up. My head's in the way. There we go. Okay. So these are both positive, so I'm just going to put positive, positive there. Okay. So now what I'm going to do is I'm going to add my x's and y's together, right? So I'm going to take those x's and y's, add them together. So 0 plus 37 is just 37. Okay. That's it. And then we got these two positive answers, 65 plus this 53 number. And I'm going to get 118.2449. Okay. So now I found my x and y's. I just had to put it back together since we're looking for it looks like we're just looking for the magnitude. There's no angle on this one. So it'd be nice if we could find the angle too. So let's do that. So I'm going to redraw this picture, right? So my resultant somewhere in between these two. So I'm going to go draw my new axis. So that's my origin. So this dot here is like this dot right here. Right? And then I'm going to draw my x and y's. So a little bit x, so about 37 there, 0.28 newtons. And then a lot of y straight up here, because they're both positive, 118 point. My head's in the way. There we go. Point. Oh, poop. Yeah. 0.2449. Okay. Now what we're looking for is that hypotenuse. We want to find out what this number is. We also I'll find the angle too. Might as well. All right. Find out what that angle is. Just because I like vectors having angles to them. So to find out the hypotenuse, I'm going to use Pythagorean theorem. Make sure you square that answer. I get 123.9. So that question mark. So I was using x squared plus y squared is equal to like my f net that we're trying to find here squared. So f net is going to be 124. There we go, 124. So it's going to be C. If you want to find the angle, tan inverse my opposite, which is the 118, divided by that 37 number. And I can easily find that in my calculator here. Make sure I put brackets around that. Well, easy enough. I just had to type all these numbers in my calculator. That's about 72 degrees or so. Okay. So it's pretty steep. Yeah. Somewhere in between. Like that's what we're looking for, that line that's like right in here. That's what we're looking for. And that's what we found, 124. Okay, let's go to the next question here. Student exerts a 85 Newton force by an angle of 40 degrees with a horizontal and vertical components respectively. Oh, it's just like this question up here. Right, it's pretty much the same thing. But now they want both the pieces, right? So if I were to draw this picture out, we got this crate here. It's being pulled at an angle of 42 degrees, 85 newtons, and we just want to find out the x and the y pieces. So remember to find the x, since that's adjacent there, so I'm going to use cos 42, and to find the y, I'm going to use sine, because that's across the triangle from the angle of 42. Okay, so 85 times cos 42 gives me 63. They want it respectively, so they want the horizontal first, and then this one. So it looks like it's not going to be this one, and I don't know if it's D. It's probably not D. No, it's not D, because that's the wrong first one. So this is going to be, what is it, 63? Yep. 167 newtons. And then it's probably not going to be this 85 because the hypotenuse is always the longest side of a right angle triangle. So it's probably going to be the 56 one here, the 57. So this is 56.876 newtons. There you go. Okay, an object shot. An angle. What's the horizontal distance it will travel before it strikes the ground? Okay, so this is a T-chart question. Seems like we've done these before. Let's double check this. Well, there's a lot of questions, that's probably why. Okay, so shot into the air from the top of a 25-meter cliff with an initial velocity of 45 at 32 degrees. what is the horizontal distance it will travel when it strikes, I'm assuming that it strikes the ground below, right? So if I were to draw what this kind of looks like, so this object shot upwards at 45 meters per second at this 32-degree angle, right? There's a height here. It's going to go down 25 meters to hit that ground, right? So if I were to draw what the picture would look like, you'd probably do something like this. It's going to start off at this angle, but it's going to lose that vertical velocity and fall down, right? And we're looking for that horizontal distance. Okay, so because there's an angle, because there's a velocity, and we're looking for horizontal distance, this is definitely a T-chart question. All right, so we got T-chart. We got two parts here. We got the X, right? We got the Y. That's the horizontal. This is the vertical. So remember, in the vertical section, we got gravity acting on it. We're going to assume there's no air resistance here. So let's say up is positive. So this is going to be negative 9.81 meters per second squared, because that's going down, right? Its vertical displacement is going to be negative 25, because it has to fall down, right? Its initial velocity, which we can find, we'll have to find it by doing the X and Y stuff over here, and we're looking for time. So the reason we're looking for time is so I can use the time over here to help me find this V, because it's going to be V times T. Remember, that's the only formula I'm allowed to use in the horizontal direction. Just V is equal to D over T. Okay. There's no acceleration in that direction. So to find the velocity, again, I got to use this little triangle over here. All right, so I pull up my triangle. I look for this X and this Y direction here. So I'm going to go 45 cos 32 degrees. It's going to find me my X. So that's going to be 32 or 38.1622-ish meters per second. And then if I do it again, I'll use sine here. 32 degrees. So that's going to be 23.8464 meters per second. Okay. So now we know our X and Y pieces. This 45 doesn't belong in this. So this is X and Y T-chart here. It doesn't belong in there, right? So what I actually need to put it here is all the components. So like this 38.1622, the X component goes in my velocity. Remember, this side doesn't have acceleration, so there's no VI, there's no VF. They're both the same. So we just say V average. And over here, my VI starts off as 23, but then it will slowly decrease when it gets to the top. So it goes all the way up to the top, and then it speeds back up as it goes down. So this is always kind of changing because of the acceleration. Okay. Then we just have to pick the appropriate formulas here. So we want to find time. So I can use the time on this side over here. So it looks like I'm probably going to want to use VD is equal to VIT plus 1/2 AT squared, right? Yep. Okay, so now we're trying to find we're trying to find time here so I can use it on the other side. The problem is time doesn't cancel out, right? So what we're going to have to do, we're going to have to pull out a calculator. We can try to use the quadratic formula. I can put the numbers in. All right, so if I did put the numbers in, while my calculator loads up, I'm going to put a negative 25 here. I have a VI here of positive 23.8464 T. I don't know what T is, plus 1/2, a negative 9.81. So technically minus, but I could just put in here what I would write. I'm going to ignore the units. They all look pretty good. Meters, meter per second, yep. And then I got T squared. So I'm looking for T here. So I'm just going to go to my calculator. I don't care about that. Okay. So we're going to put in a few things here. So my Y is equal to, got to get rid of some stuff that's there before. I'm going to graph the two sides of my equation. So for the first side, I got the negative 25 there. So I'm going to graph negative 25. And the other side is I'm going to graph this 23.8464t. But I can't use t, so I could use x's. All right. Oh, it's 8464. Let me just change that. 8464. And then over here, I'm going to go plus a half times negative 9.81 times x squared. Let's see what that looks like. So that's what it looks like there. Okay. So instead of t's, I got to use x's. Make sure that one's squared. I got a negative there. Got a negative on that. Yep. Okay, so now if I hit graph on this, I got this line that goes up and then comes back down, because that's what it kind of looks like. It's supposed to go up and then come back down, right? And then I want to hit the bottom. The bottom is at negative 25. So what I'm going to do is I can either zoom out or I can fiddle with my window. I kind of like fiddle with my window a little bit more because you have a little bit more control. Zoom out just zooms out in every direction. So I just want to make sure I get to the minimum, which is at that negative 25 mark. So I'm just going to go negative 30 because I want to go past that. So there's that line. So let's go up, down. You may want to see at the top of the graph too. So if I make my y max here just a little bit more than this, let's go 20. You might be able to see it. Nope, can't see it. I'm going to go a little bit more than that. Let's go to 30. Oh, there it is. Okay. So there's my graph. So it starts here. This is the top of the cliff. Going up, 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 hit the top, down, 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 down. Then this is where I want to know where it hits the ground. Okay? So this is not a distance axis, right? This is the time axis. So I can find the time at which it hits the ground. So I'm going to go second, trace, 5. 5 is intersection. And there's only two graphs, so enter, enter. And then I'm just going to guess, I don't know, 1, 2, 3, 4, 5, 6. I'm going to guess 6. So when it says guess, you could just type a number in. You can move your cursor over there. I'm just going to type in 6. So there's my intersection. 5.71, or sorry, 5.7483. Okay, so let's move this out of the way. So we just found the time to be 5.7. I just forgot that number. 7483. 483 seconds. Okay. Then I could take that time over to the other side now. Put it over here to find my distance. So this is just going to be v times t. I got my v, that 38 number there. I'm just going to times it with my time. So 38 point, times it with a 5.7483. And I get 219. Yeah, there it is. Okay, so that's D on this question here. So 219.368-ish meters. Proper sig digs. They only want 2 sig digs here, so scientific notation, 2.2 times 10 to the 2. Cool. There you go. That was a tricky question because you had to use a calculator to find that time. You could use the quadratic formula, but since there is no way to, because there was no d is equal to 0 or vi is equal to 0, there was no way to remove a t from this equation. So we just left it. All right, for an object to fall and have a parabolic projectile motion, the motion must be influenced by a vertical force of gravity. By a vertical acceleration that decreases. That doesn't make any sense. Displacement, that's constant. No, that doesn't make any sense. Vertical velocity is not constant, right? My vertical velocity is always changing because we're accelerating due to gravity. All right. Okay, for some reason I couldn't. Got to move this around to my way too. Okay. Acceleration is not changing, right? So acceleration stays the same. It always stays at 9.81. So it can't be that one. So this doesn't make any sense. That doesn't make any sense. That doesn't make any sense. So a nice constant force of gravity, and the horizontal velocity has to remain constant, just like we had up here. We had a nice constant acceleration, 9.81, and the horizontal side stayed nice and constant, right? There's no acceleration there. The value of Newton's gravitational constant was first calculated by using, a torsion balance, actually. Remember that one? That's that weird device I showed you. Had these really big masses here on both sides. You got a mass on that side, you got a mass on this side. They were balanced on here, so then they would twist, right? Because there would be another massive object here, right? And then these objects would be attracted towards each other or repelled, but in this case attracted because we're talking about gravity. So they would be attracted. So there'd be this force of gravity which would twist this wire, and in this case it would twist that direction. And then when it twists, you would determine the force of gravity, right? There might be a little mirror here where a little light will reflect off it, and then you can measure, right? You can measure the angle, measure the force, essentially. That's what you're measuring. And then you can use that to find G. Deflection of light during a solar eclipse, no. Acceleration, no. None of these, okay, yep. Okay, a student made an inference about the motion of an object traveling in a circular motion. Okay, so the speed of the object changes. No, that's not true. The speed of the object doesn't change. So that's a false statement. That's not good. Speed is constant, right? Well, in this course it is. Yeah. Object is accelerating. That's true, definitely, because we have an AC, right? Right, definitely an AC. It's like equal to either v squared over r, or it's equal to 4 pi squared r over t squared. So that's definitely a true statement. The velocity is not constant, right? Velocity is always changing because you're always changing direction. Always changing direction, right? And the velocity vector is tangent to the circle. That's true. Yeah, it's dependent on the circle, right? So, or not dependent on the circle. Depending on where you're on the circle, depends on which way it's pointing. But my velocity vector will always be a tangent to that circle, right? So those are my velocity vectors, right? It's always changing direction as you're moving around the circle. So what's true here is 2 and 4. 2 and 4, there we go. Cool. Okay, so we got this so we're moving into the circular motion stuff here. It's kind of fun. A test tube in a centrifuge is traveling at a velocity of 40 meters per second with a radius of 35 centimeters. What's the period of the tube? Okay, so VC. Remember, there's a bunch of formulas for AC, but since we have circular speed here, we probably want to use the VC formula, which is just 2 pi r over t. Don't forget that formula. That exists. We can use that for circular motion. You could probably try to use the other two formulas, but they have a bunch of squares and stuff in there. We don't want to do that. So we're just looking for t here. So I'm going to rearrange for t. It's going to times the t up to the other side, divide the VC down, right? I'm not going to show all those steps. At this point, 33 questions in here, we should be probably pretty good at rearranging. And then we just put all the units in, or the numbers in. We got 2 pi. We got a radius of 35 centimeters. But I'm going to change that to meters. Important, right? And then, because the other one is also in meters per second, so you want to make sure those units match each other. All right? And then we punch all these numbers in a calculator. We are only divided by one number, so we don't have to worry about like brackets and stuff on this one. We just have to make sure, change that centimeters though. This will be in seconds. You can notice the meters will cross off here if you do some unit analysis. So meter divided by meter. So I'm left with the seconds, but remember that's the denominator. My denominator becomes my numerator, so that's in seconds there. And because I'm going to move the decimal place over 2 spots this way, I've got a negative exponent, so it's going to be A. This is weird. Why would it tend to the 0? That's weird. I don't know why you ever do that for scientific notation. All right, so we got this one here. An engineer designed a road. What's the minimum radius of curvature we can have here? Okay, so they're giving us a force here. So if I list off what we have here, like this is my force here. So we required this force, Now, the force as you move around here, the force that's keeping the car in the circle is the force of friction, right? That's centripetal force. Right? So this here, this 1,470 newtons, that's keeping the car in the circle. We have a mass, 1,250 kilograms. We have a speed, I'm assuming a circular speed because it's going around the curve, of 80 kilometers, but I'm just going to divide that by 3.6. All right, so we get 22.222 meters per second. Bunch of twos there. Yeah. What's the minimum radius? So we're going to find a formula that involves radius. We're looking for r. All right. So remember, FC is the same thing as an F net, so it's equal to mass times acceleration. But because this is FC, this is A is the AC. Remember that. F net is equal to mass times acceleration. Okay? So we got mass times AC, and AC, from our formula sheet, is one of two things. It's either V squared over R, or it's equal to 2 pi squared R over T squared. We're looking for R, and we have V. So we're going to use the V squared over R version of that formula, times the R up, divide the FC down. So we're doing a little swap there, and there we go. That's it. Just put all the numbers in this formula. We don't have to change any of my units, except we changed the kilometer per hour already. So let's just do that. Make sure to square. This is very common to forget to square your speed here. And then divide by my force. So we get 419.9. Seems weird that this answer is not rounded properly. Because it should be, if I round this properly, 420 meters. None of those are 420. Oh well, just the way it happens to be, I guess. Let me just double check. 80 divided by 3.6. I'm going to square that. I'm going to times by the mass. I'm going to divide it by the force here. Yeah. I'm not happy about that one. I probably should. I got to vet these questions a bit more. Okay. So an object is moving in a circle at a radius of 60 meters per second, 60 meters at a speed of 20 meters per second. Oh, it's tripled its speed and the radius of the circle is doubled. What is the original? And by what factor has this changed? Oh, that's weird. Okay. So they want us to do the math on the original one. So just using these here, what's my centripetal force? So just using the original numbers here, because they want to do what the change is. It's either going to change by 1.5 or by 4.5, but they kind of want to know what the original was. So it's going to be mass times acceleration, mass times V squared over R is equal to FC. So I can just do this math here. Kilograms, meters per second. Yep. So just put the numbers in. Not too bad. Let me just do this really quickly here. So I got 100. It's 100 newtons. What are these other ones? That's weird. Why would they be like that? Oh, if you forget to square the V, they put the 5 in there. Okay. So we cross off A, because that's the wrong one there, and you cross off B, because that's the wrong one. So now we have to determine the factor change. So remember, this is one of my favorite kind of questions. So I want to know what happens if I change the other things. So if I triple the speed and double the radius. So triple the speed. And I double the radius. Okay, so I can see where the 1.5 comes from. The 1.5 comes from the mistake of not squaring the change as well, right? So this 3 that's inside, the speed is being squared. It's like proportional to the square of the speed. If I triple the speed, I got to square the triple. So I square that, becomes a 9 mass v squared. So I pop the 3 out here by squaring it. And then I got the 2 and the r on the bottom. So these are my new numbers here. So these are the numbers I care about in this question. All right. Everything else is my old numbers. So this is 4.5 times everything that's old. So the answer is going to be D, because that's the right 4.5 there. There you go. I love those kind of questions. The gravitational force between these two guys, so that's not too hard to do. When they're 7 meters apart. Oh, the student and her car. That's weird. Okay. So to find the gravitational force between two objects, we have to know the mass of two objects and the distance between them squared, right? So this is an inverse relationship. The further apart they are, the weaker it's going to be squared, right? Inverse proportional to the square of the distance between them. Capital G is the 6.67 times 10 to the negative 11 number. That's on our formula sheet. We got 63 kilograms. We got 1,400 kilograms. Kilograms are what we need. You look at the units of G, they're in kilograms. They're not behind me. Okay. And they are 7 meters apart squared. So probably one of these answers is if you forget to square that number. Okay, let's see. Yeah, no, they didn't. They didn't put that one in there. 1.2 times 10 to the negative 7. 1.2006 or so times 10 to the negative 7 newtons. So that's going to be C. Cool. On planet, which has a radius of this, is dropped. What's the mass of the planet? Okay, so what they're trying to do here is they're trying to say, okay, what makes the rock drop, right? So what's causing the rock to drop is this force of gravity, right? So that means my F net is, I'm assuming there's no resistance here again, is equal to Fg. How do we calculate Fg and F net? Well, it's mass times the acceleration, mass times gravity. The masses here are the mass of this rock. They don't give us that information because we don't really need it. Because if I drop this calculator, I don't need to know its mass to figure out all this information, which is something that just cancels out. So what is G? Well, because we're not on Earth, we don't know what this G is. So we're going to use Gm over R squared to help me calculate what that G is. And that's what my acceleration is going to be equal to. So that other m that I just reintroduced here, this is what's causing this field, right? So this is the planet. This other rock, or this other mass, is the rock. That cancels out. So that's what we're looking for. We're looking for that m there. So a times r squared divided by this capital G. So what's a though? All right, that's what we need to find. So what I need to do is I have to use this other information that this drops from rest. So VI is equal to 0. It takes 0.8 seconds to reach the ground, right? It falls 6 meters. Find the acceleration, right? So I just have to find a good formula that has these three things in it, which is going to be D is equal to VIT plus 1/2 AT squared. But remember, if I have some zeros, put those in first. So 0 times T is going to be 0. So that whole first term just disappears, which is kind of nice in our calculation here. To find A, to get rid of the half, I'm going to times by 2. And then I'm going to divide by T squared. Okay, so there's my A. So A is 2 times D, so 2 times 6, and make sure all the units are right. That looks pretty good. Divided by 0.8 squared. So my acceleration due to gravity on this planet is 18.75 meter per second squared, bigger than Earth. Okay, so now what we're going to do is we're going to take that and put it over here, right? So I'm going to do this step first, and then we're going to come back here and do this second, right? So I do all that to find what the A is, come over here, plug into this equation. So that's what this radius is for, right? The radius is for the radius of the planet. So I'm going to put that number in there, 6.2 times 10 to the 5. I'm going to square that. Oh, I don't like this calculator. Don't trust it. Okay. I'll square that, and then divide by big capital G, 6.67 times 10 to the negative 11. Remember, if you divide it by something that has scientific notation in it, like times 10 to something, either use the E button in your calculator, or brackets, or the fraction button. You just want to make sure that stays as one number and doesn't separate into two different numbers. So here I get a mass, which looks good for the mass of this planet. It's a much smaller planet than Earth, so the mass doesn't have to be as big, but it is still pretty big, times 10 to 23. 1.1 if you go prop 2 sig digs here, 1.1. There you go. Cool. Next question. Where are we right now? 40. Okay, so I was going to go up to 40, stop this video, and then start a new video. You could see my program is already slowing down on me with all this writing that I'm doing on here. Okay, so we're going to, okay, after these 6 questions, I'll stop this video. So use the following for the next 6 questions. So we got these two, I don't know why they didn't just use a D there, okay, or radius. From the surface, from the center of the Earth. So that's a radius. So that's R. Right? I don't know why they use an S there. Because it's from the center. So center to center, that's a radius. That's good. The mass of the satellite is 100 kilograms. Probably not useful. The mass of the next satellite is 50 kilograms. Not going to be useful. The mass of the Earth is that. No, it's not, but we'll just use it. Remember, it's 5.97 times 10 to the 24. It's on your formula sheet. And the speed of the satellite is 7,700 meters per second. Satellite 2. Okay. Which vector is the direction on M1 at this point? The direction of the acceleration. Remember, the acceleration is proportional to the force. So they are proportional to each other. That's Newton's second law. So whichever direction the acceleration's in, that's the direction of the force. So if the force is inwards, so we're doing this on object 1 up here. So if the force is inwards, that's gravity, then the acceleration must be inwards as well. So it's got to be that way. Okay, the orbital speed compared to that of 2. Okay, are they both the same? They're the same. Yeah, because mass doesn't matter, right? It's all about the mass of the planet and the orbit from the planet. If those two things are the same, then my speed stays the same. And I'll just show you that here in the calculation. That if I do this, I go FC is equal to FG, MAC is equal to MG. The mass of the satellites cancel out, right? The masses are gone, right? So then it just becomes a formula where it just does this. If I just go over here, which I might need this for later, I'll just do it here. So AC, I can use the V squared over R. Little g is not 9.81, even though we're talking about Earth, we're not on Earth, so we have to calculate it. So if I rearrange this for V, the only thing that determines what V is the gravitational constant and R. The gravity of the planet and R. This is Earth. Right. So the mass is gone. The mass of the Earth is the only thing I really need. So cross that off, cross that off. So constant. It's the same. As long as you don't change the radius, it's the same. Because it'd be weird if they had different speeds, they would collide into each other eventually. Because they hit each other. They're going the wrong way too. You have to make sure they're going in the same direction. Okay, the centripetal acceleration of m to the is closest to what? Okay, so it's not going to be 9.81. Actually, Depends on the distance, it might be. Yeah, who knows? We can go through here and try to figure out what that is. That's little g, right? Which is just going to be gm over r squared, right? Because that's, if I look up here, that's what that is, right? AC is equal to g. AC is equal to g because I did this whole FC is equal to FG thing, right? Crossed off the masses. So I just had to do this calculation. G, 6.67 times 10 to the negative 11 times the mass of Earth. I'm going to use their mass because why not? 24, 6 times 10 to the 24, and divided by the radius that they're using here. The radius of orbit here is, that's 6.7 million squared. It's actually 8.9. Where's that? Oh, 8 point. Yeah, that's kind of weird. Closest, I guess 8.8. All right, gravitational force acting on M2. Well, gravitational force is just going to be mass times gravity. And the gravity is a 8.9 number, or 8.8. And the mass of M2 is 100. Oh. So times it by 100. You get 891. That's better. Yeah. It's strange that they say this is closest to and this is closest to, but they didn't put 8.9 up there. That's very strange here. Now I hope that one of them is not the other one, like the 50 kilograms, because that would be a pretty piss poor choice there. Yeah. Earth does no work on the satellite because, why? Momentum is constant? No, not constant because, well, we don't talk about momentum in this course, but momentum is a vector. It's always changing. Velocity is moving at, no, it's not moving at constant velocity. It's constant speed. There's no force on the satellite. Doesn't make any sense. The gravitational force is perpendicular to its displacement, yeah, because it's always perpendicular. Right? Because if the force, if I'm moving this way and the force of gravity is this way, they're not going to affect each other. They're going to change the direction, but they're not going to change that thing. Yeah. So there's just no work done to it. So it's got to be D on that one. Okay. If a third place were placed in a circular that was greater than R from the Earth, its velocity would be less, would be lower, right? Because V is equal to the square root of GM over R. We look above, right? That's how we found that. And if this goes up, this is going to go down. Inversely proportional to the square root, but they're inversely proportional to each other. Let's talk about speed, right? Yeah, velocity. Cool. Okay, so I'm going to stop this video here. I'll see you in the next. Bye.